Okay, so compound, it's called manipulation of percents, but they're going to get into compound interest. So let's do this first. Let's go over to our notes page. And we know what so this is based on exponential growth, right? So exponential growth if you remember, is, the amount at the end of some amount of time is equal to the initial amount times, we did 1 plus the rate to the t power for time, right? So we're going to use this formula for compound interest. We're going to modify it just a little bit, okay? So for compound interest, it's not wildly different. It's going to look like this. A equals P. Now, P stands for principal, right? That's like the initial amount you put into, so like a savings account or a CD or something like that, times 1 plus, and here's a slight little difference, R divided by N to the NT. So it looks a little bit like what we have up top there, right? So I'll just define what these variables mean, right? So A, that's some final amount, right, after some number of years being invested. P, that's like the initial amount originally, right? But that's, when we talk about finances, that's called principal, right? The initial amount you put into some investment, okay? R, that is the annual. That says annual, by the way. And UA, that's the annual interest rate, right? Again, converted from percent to a decimal, okay? Now, N, that's the number of compounding periods per year. Okay, so if you put money into a savings account and they tell you it's compounded monthly, then what would the value of N be?
The number of years.
Well, no, N is the number of compound. If you're compounding monthly, what is the value of N? How many months are in a year? 12, right? So N would be 12, okay? And of course, T is time in years, okay? So the interesting part of here is like the R is the annual, the yearly interest rate, okay? But if we take this R and N and divide them, so let's say it's 12% per year, how would you figure out the actual monthly periodic rate? It would be 12 divided by 12, it would be 1% per month. Does that make sense? Okay? So this R and N, when we do this thing to it, R, the annual rate divided by N, that equals what we call the periodic rate. In other words, you just take the yearly, the annual rate, and you divide it by the number of compounding periods per year, and that's that periodic rate. Again, if it's monthly, you divide the annual rate by 12. If it's weekly, how many weeks are in a year? Come on, somebody knows. How many weeks are in a year?
52, right?
52, right?
49.
52. So if it's compounded weekly, you take the yearly rate and divide it by 52, and that gives you the weekly periodic rate. And there's other divisions we'll get to on the next section. Okay? So that's our compound interest formula. Yeah? Question?
Can you scroll up on the notes?
Yeah. You guys need time to write that down?
All those. I think that was the top one.
Up here?
Okay.
Yeah, I just, this formula we have already, the exponential growth. But compound interest, you can see it looks like exponential growth with just a couple of tweaks to it, right? But it's still exponential growth, right? Which is great when you're dealing with money. You want your money to grow, okay?
Mhm.
All right, so everybody have this? We go back to the notes. All right, so let's look at some examples. And they're not all these examples are compound interest, but we'll get into more of that here in the next section. So this first one here says Jen puts $500 into a savings account, right? That'd be our principal, wouldn't it? And it earns 6% annual interest. There's our R, annual rate. So they want us to write, okay, so the compounding is only once per year, right? Did everybody catch that? They want us to write a formula. So P, principal is 500. R, it's not going to be 6. What are we going to use for our R? Our R. Not 6, but what?
0.06.
0.06.
0.0.
And they're compounding once per year, right? So what is the value of N?
And it's 1 year.
Just 1, right? And like in that formula, if you divide by 1, are you really changing anything?
No.
Yeah, so technically this isn't really compounding, so to speak, but, you know, on a mathematical level, we could say, okay, it's just compounded once per year, right? So our function would be C of t, as they want, equals, what would it be? What's the P comes first, right? And that formula I gave you a minute ago. What am I going to write here?
500.
500.
Parentheses.
Yep.
1.
1.
Plus 0.06
Divided by
1.
1 to the
Parentheses.
1 times t, right?
Yeah.
All right. But you guys all understand those ones don't really affect anything, right? So we can simplify this, couldn't we? C of t is just 500 times 1.06 to the t. Okay? So it's only compounded once per year. Well, let's look at the follow-up here. Now they want us to write a function that approximates the amount of money in her account using a monthly growth rate. Monthly, how many months in a year?
12.
So n equals 12, right? So it'll adjust our formula a little bit. So C of t, still going to be 500, right? Times 1 plus 0.06 divided by what?
12.
12 to the what?
12.
12t. Okay? So now we have to calculate the 0.06 divided by 12, right, to simplify this. So C of t equals 500 times 1 plus, anybody know what 0.06 divided by 12 is? Whoops, I didn't want that. Let's go to scientific. You guys see my calculator?
Yeah. It's 0.005.
Divided by 12. 0.005, right? 1 plus 0.005 to the 12t. And of course, we can simplify that, streamline it a little bit. 1.005 to the 12t. Okay? Anybody have any questions on that? Just being able to write, you know, the equation for the growth and the interest. Okay. Let's move on to the next one, which is not money. This is something about black bears here. Okay. Study of black bears in Adirondacks reveals their population can be represented by this function, P of t, population, 3,500 times 1.025 to the t. So, guys, looking at that formula, how many black bears did we start with?
3,500.
3,500 of them, right? And they grow, I would say it looks like 2.5% per year, right? So T is a number of years. So let's write this function here, right? Oh, and by the way, this is a monthly growth rate, right? So what does that equal?
N equals 12.
Again, right? So let's work out the formula then. So P of T is going to be our 3,500 well, let me do it this way. This will be simpler. Let's just take that annual rate and figure out what it should be. Let's take the 0.025 and do what to it? To get
Divided by 12.
divided by 12. And if you punch that in your calculator, you should get 0.00208. Right? Are you with me? So now I can just write the formula, right? So P of T would have to be our starting number of bears times 1 plus this amount would be 1.00208 to what power?
To the power of 12T.
To 12T. There might be a typo here. Should that be 08 at the end there? Anybody check that? Let me just look and see. 0.025 divided by 12. 0.028. I think they have a typo in their thing here. So it should be like choice 1, right? This 6 here, that should be an 8. You guys agree with that? Little typo. All right. So we went from annual to monthly again. In the next section, we'll do some other compounding periods, but we're kind of keeping it simple here. All right, next one, studying public policy, modeled Detroit's population. So the population decreased 25% over a decade. How many years are in a decade, guys?
10.
10. And it decreased. So is this growth or decay?
Decay.
Okay. Hey, if it decreased 25%, how much was left? What percent?
That'd be 75%.
Okay, so here's the formula they used, right? What was the starting population?
Our population was 714.
Well, okay, but let's be careful. There's more than 714 people in Detroit. You see what I'm underlining here? How many people did they actually start with there in Detroit? Not 714. 714,000 people. Okay, does that make more sense? Even if you don't know much about Detroit, hopefully you know it's a fairly decent sized city, right? There's a little more than 714 in Detroit. Okay, so this is a model in decades, like every 10 years after 2010. Okay? Now, read this very carefully. There's another student, Suzanne. She wants a model that would predict the population after every Y years. Not decades, but years, right? So for us to go from decades to years, what would our N have to equal to get that periodic rate? How many years are in a decade? 10, right? So let's get the rate that she would use. Okay? So what are we going to do to get the rate she would use? He used 25%. How is she going to calculate her rate to switch this model to a yearly model instead of a decade model? Take the 25% and do what with it?
Move it.
Move it. I guess you meant divide by 10,
Yeah.
right? And you can divide by 10 easily, just, you're gonna move the decimal once to the left, right? So wouldn't that be 0.025? Right? Okay. And so it's going to be Y years, right? So what's the model going to be? It's going to be P equals what?
P equals
714.
714 times what?
times 1 plus,
Careful, it's
I don't
decay.
know, 1 plus, it's decay, so it's just
Minus.
Minus 0.025, right? To the Y they're using. So that, and that makes sense, right? If the original model was in decades and it went down 25%, it's going to go down less than that every year, right? So only like 2.5%. But let's do that subtraction. And what do we end up with? P equals 714 times what? Point. Nobody have it? 1 minus
yeah, it's
0.025.
number, it's 0.9750.
Yeah, well, we don't need the trailing zero, right? Okay. Well, they did put the trailing zero in there. It wasn't really necessary. Okay. All right, so it'll be choice 4. Anybody have any questions on this one? Okay, so we kind of started looking at the compound interest formula, and they got a little sidetracked with it here, but that's okay. The next section we'll get more deeply into compound interest. So let me stop this video real quick.